Imagine you wake up and send a message without saying a single word. Imagine you learn a new language without studying, compose a melody without touching an instrument, or solve a complex problem without pen and paper. Imagine your thoughts are no longer fully private, but can plug directly into digital systems. Now imagine this is not science fiction, but history. In the year 2072, people talk about neural interfaces the way they used to talk about smartphones. Normal. Boring even. But the road to that normal was long, messy, and full of plot twists. NVIDIA sat right in the middle of that story, not by putting chips inside brains, but by providing the compute that made brain signals readable for machines. To understand how we got here, you have to go back to the decades when biotechnology, artificial intelligence, and neuroengineering started to overlap. In the decade of the 2020s, brain-computer interfaces already existed, mostly for medical use. Companies like Neuralink got the headlines. But the field was much broader than the media made it seem. University labs were designing electrode arrays. Research institutes experimented with new materials for implants. Hospitals ran trials where signals from the brain were sent directly to robotic limbs, bypassing damaged nerves. Those systems were clunky, slow, and experimental, but they worked often enough to prove one thing: the brain could talk to machines. At the same time, AI was getting very good at one thing: pattern recognition. Models learned to classify images, transcribe speech, translate language, and predict sequences. NVIDIA's GPU clusters were the engines behind a huge share of that progress. Their hardware and software made it possible to train bigger and more accurate models. In the beginning, nobody connected that to the human brain. It felt like a tool for big tech, not for neurology. But behind the scenes, some researchers were already asking a wild question. If AI can decode pixels and sound waves, why not neural signals? In the early years of the decade that began around 2030, that question turned into a concrete research program. Scientists discovered that certain patterns in neural activity were surprisingly consistent. A thought does not have a fixed shape, but the electrical patterns that ride along with it are stable enough to be recognized. With enough data and enough compute, AI models could begin to map those patterns to intentions, movements, and later even words and emotions. At that point, NVIDIA's role expanded. It no longer just provided chips. Its GPU clusters became the training ground for models that could, in real time, translate brain signals into digital actions. The first big visible breakthrough came around the year 2037. Neural interfaces reached the point where users could write text without typing. It was slow, often imprecise, and limited to short phrases at first. But the experience was magical. People would sit in a chair, focus on words, and see those words appear on a screen. The devices were branded under various neurotech companies, so normal users never thought this was NVIDIA. But under the hood, those systems depended on AI models trained for thousands of hours on NVIDIA hardware. Those models had learned to separate noise from signal, random spikes from actual intent. After that, adoption moved faster than even optimists expected. By the early years of the decade, starting around 2040, neural interfaces were reliable enough to fully replace speech for people with severe disabilities. A few years later, they started appearing in early consumer products aimed at gamers and creatives. The pitch was simple: control digital worlds with your mind. No mouse, no keyboard, no controller, no touchscreen. The same hobby that once pushed demand for better graphics processing units became the testbed for mind-based control. Gamers noticed they could aim, move, react, and communicate with less friction. That feeling of no input lag was addictive. NVIDIA benefited indirectly. Every neural interface needed fast, accurate decoding on the back end. That meant models running on edge accelerators, on local servers, or in low-latency data centers. The difference between "this feels like telepathy" and "this feels annoying" was a handful of milliseconds. NVIDIA poured effort into network optimizations, edge compute, and new accelerator designs tuned specifically for these kinds of workloads. The real shift, though, came around the middle of the century. Up to that point, neural interfaces were mostly seen as assistive tools. They helped people with paralysis, gave new input methods to gamers and creators, and offered alternative communication channels. Around the year 2050, the story changed from helping to enhancing. The models that interpreted neural signals became far more sophisticated. AI could pick up on emotions, levels of focus, and abstract intentions. Implant technology improved as well. Devices became smaller, safer, and less invasive. The public debate shifted from "who would ever want this?" to "why would you not want this if it gives you an edge?" For the first time in history, there was an interface faster than language and more precise than body language. People could interact with systems at the speed of thought. You did not have to search for words, you just had to intend. That possibility opened doors nobody had carefully planned for. By the mid-decade that followed, neural interfaces went mainstream in certain jobs. In creative industries, they were almost expected. Composers could sketch entire harmonic structures in their heads and have AI render them into full arrangements. Designers could sculpt three-dimensional forms by imagining shapes and flows, instead of wrestling with a mouse or stylus. Engineers and programmers could structure logic in their minds and let the system turn it into working code. NVIDIA's position in all this was similar to that of power utilities in the Industrial Revolution. The average person did not think, "Thank you, NVIDIA," every time their neural interface worked. But without the compute stack behind it, nothing would have moved. As with every big leap, a shadow side appeared. In the decade of the 2050s, the debate about privacy and control grew intense. If sensors could read intentions, what did that mean for autonomy? If neural patterns could be logged, who owned that data? Governments worried about interrogation and surveillance. Companies worried about liability and consent. Some countries banned non-medical neural interfaces altogether. Others offered tax breaks to companies that encouraged their use. A new geopolitical front opened up: neural sovereignty. Who had the right to collect, store, and process brain-derived data? NVIDIA once again found itself in the uncomfortable role it knew from earlier decades, an infrastructure provider caught in the middle of ethical and political fights. Around the year 2060, another boundary was crossed. Neural interfaces stopped being just input devices and became feedback channels. AI models began feeding context back into the brain in subtle ways, not in the crude science fiction sense of full sensory simulations, but as guided reinforcement. People with neural augmentation could learn faster, recall more, and connect ideas more effectively. Language learning accelerated. Technical training compressed. Complex, multi-step analyses became more manageable. The line between using a tool and being extended by a tool blurred. On the compute side, that shift created an entirely new class of workloads. Neural signals had to be turned into vectors. Those vectors then passed through language models, visual models, emotional models, and decision models, all running with extremely tight latency budgets. Output had to be shaped so the brain could integrate it smoothly. This required huge amounts of compute, but also a very different performance profile than classic data center or gaming tasks. NVIDIA responded by designing accelerators optimized for neural interface pipelines, with short, predictable delays and tight integration between local and remote compute. As adoption spread, a new social category emerged: cognitively augmented users, people whose neural interfaces gave them access to faster thinking, deeper recall, and richer support. That was controversial. Some critics saw it as a new kind of inequality. If only a subset of people could afford or access augmentation, they would gain a long-term advantage others could never close. Supporters argued the opposite, that augmentation could level the playing field if deployed widely, helping people overcome disadvantages in education or health. Different countries made different choices. In some professions, augmentation became a requirement. In others, it was restricted or heavily monitored. But technology has a habit of leaking out of the boxes we try to put it in. Over the next decade and a half, neural interfaces kept getting smaller, safer, and cheaper. Implant-free versions with high sensitivity appeared in headsets, glasses, earbuds, and even skin patches. By the time the world approached the year 2070, hundreds of millions of people used some form of neural interface in daily life. Many did not even think of it as neurotech. It was just how you interacted with the systems around you. By then, NVIDIA was no longer described primarily as a chip company. It had become a cognitive infrastructure provider. It supplied the compute platforms, frameworks, and connectivity that allowed neural ecosystems to function. It did not decide what people thought. It did not write their ideas. But it made sure those ideas could be captured, processed, and mirrored back in ways that felt fluid and natural. From where we stand now, it is hard to imagine the world of the year 2020, where humans hunched over glass screens, pecking messages out with their thumbs. It feels slow and awkward, the way quills and ink felt to people in the typewriter age. But that old world is an important reminder. Every revolution starts out looking like a toy, then a luxury, then a risk, and only later a necessity. The revolution of neural interfaces was not a single explosion. It was a long evolution, built out of tiny lab experiments, policy debates, product launches, and cultural fights. NVIDIA did not set out to change what it means to think. It set out to build faster chips and better performance. But by enabling the decoding and shaping of brain signals at scale, it helped build a world where the boundary between biological and digital thought is thinner than ever. And that might be the deepest lesson of this whole story. Technology does not stop at the skin. In many ways, it begins there. Sometimes it changes how we live. Sometimes it changes how we work. In rare cases, like this one, it quietly changes what it means to be human at all.